Hi everyone, my name is Roman Kuchik. Today I will present my project proposal titled Predicting Jet Engine Remaining Useful Life Using Machine Learning. This presentation is created for the Artificial Intelligence class CS540. Let's start. In this presentation, I will first introduce the general idea of predictive maintenance and explain why it is important for jet engines. Then I will move to the problem statement, where I will define the main problem this project is trying to solve. After that, I will describe the dataset used for this proposal, the NASA turbofan engine degradation dataset, and explain what kind of information it contains. Then I will briefly discuss the mathematical and machine learning formulation of the task, including the concept of remaining useful life, or RUL. Next, I will present two proposed machine learning models, such as linear regression as a simple baseline model and gradient boosting regression as a more advanced model. I will also explain why these two models were selected. And finally, I will discuss the evaluation plan, the expected practical value of the project, and the conclusion. The main goal of this presentation is to show how sensor data and machine learning can be used to support better maintenance planning and reduce the risk of unexpected engine failures. Let's move to introduction. This document describes a project proposal and basic design for a machine learning system. Actual implementation and coding are not included in this scope. Jet engines are complex machines that work under high pressure, high temperature, and constant mechanical stress. Over the time, parts of the engine naturally wear out because of the repeated use, environmental conditions, and general wear. If this wear is not noticed early, it can cause unexpected failures, expensive repairs, flight delays, or even safety risk. Traditional maintenance usually follows fixed schedules or manual inspections. While these methods are useful, they don't always show the real condition of each engine. Some engines may need maintenance earlier than was planned, while others may still be in good shape. This shows the need for a more data-driven approach. Predictive maintenance uses sensors data and machine learning techniques to estimate the future conditions of the equipment. In the context of the jet engines, sensor reading collect during operation can be used to detect patterns of degradation and predict the engine's remaining useful life, which is RUL. So RUL represents the estimated number of operating cycles left before the engine reaches failure. The goal of this project proposal is to describe a machine learning approach for predicting jet engines RUL using historical sensors data. So let's speak about the picture that we have here, predictive maintenance workflow. This diagram shows the overall process of the predictive maintenance of an aircraft engine. The engine collects operational data through sensors like temperature, pressure, vibration, rotational speed, fuel consumption, and other parameters. Data undergoes processing like cleaning, noise filtering, normalization, and feature preparation for the model. After that, a machine learning model is trained on historical data and tries to find patterns related to the engine degradation. Based on these patterns, the model predicts the remaining useful life, which is our RUL. That's how many operational cycles or hours remain before potential failure. The final stage is the maintenance decision. Engineers use the model's forecast to plan maintenance in advance, replace parts, and avoid unplanned downtime. An important part of the diagram is the feedback loop. After each new engine operation cycle, new data becomes available, which can be used to improve the model and increase the accuracy of the future predictions. Now that we understand the general idea of predictive maintenance, let's define the specific problem this project is trying to solve. Problem statement. The core problem is to predict the remaining useful life a jet engine using historical sensors data. Instead of waiting for the engine to fail or just following fixed maintenance schedules, this machine learning system will look at the sensors data and estimate how much life the engine has left. This will help maintenance team plan repairs earlier and make better decisions. We have a diagram here and let's dive into it. So this diagram shows how the engine's condition slowly gets worse as the number of the operating cycles increases. The x-axis shows the operating cycles and the y-axis shows the health index or performance, which is a measure of the engine's condition. The blue line shows degradation. At first, the engine works almost perfectly, but over the time, its performance drops. The red line is the failure threshold, the level at which the engine is considered close to failure or unsafe to use. The blue dot shows the current engine cycle. The distance from the current cycles to the estimated failure points is called RUL, which is remaining useful life. This is what our machine learning module predicts how many cycles are left before the engine reach critical states and stuff like that. This project proposes using the NASA CMAPS turbofan engine degradation dataset, which is also available through Kaggle. The dataset was generated using NASA's commercial modular air propulsion system simulation and commonly used for predictive maintenance and remaining useful life predictions tasks. It contains simulated run-to-failure data for multiple turbofan engines operating over time. Each engine is represented as a separate unit and is observed across many operating cycles. At each cycle, the dataset records several types of information. In the training data, engines are observed until failure. Okay, let's dive into the pictures we have. This illustration shows how the NASA CMAPS dataset is organized, which we use to predict the remaining useful life. It helps to understand not only the data format, but also how the information is arranged for training model. Picture number one, that one, sample dataset records. It shows example rows from the dataset. Each row represents one specific engine at one specific operating cycle. The table includes the engine ID, cycle number, operating settings, several sensor readings, and RUL, the number of cycles left before failure. Picture number two, multiple engines, many cycles per engine. That shows the data structure on a bigger scale. The dataset has many different engines, and for each engine, there is a sequence of operating cycles over time. At each cycle, the operating settings and sensor values are recorded, so the model can analyze how the engine's condition changes as it degrades. After understanding the structure of the dataset, we can now define the prediction task more formally using the mathematical and machine learning notation. For each engine, if the failure cycle is known, RUL at a given current cycle can be calculated by that formula, where C failure is the cycle at which the engine fails, and C current is the current operating cycle. For example, if an engine fails at cycle 200 and the current cycle is 150, Then the RUL is 50 cycles. Engine degradation can be represented as a gradual decline in the engine's health condition over time. A simplified degradation function can be written like this, where h of t is the engine health at time of cycle t, h0 is the initial healthy condition, and d of t represents accumulated degradation. In practice, the true health value is not directly observed. Instead, the model estimates the degradation patterns from the sensor readings, such as temperature, pressure, vibration speed, and fuel flow. From a machine learning perspective, this project is formulated as a regression problem. The inputs are the engine's operating settings and sensor readings at each cycle, and the output is the predicted RUL, where axes are inputs features from the dataset. The objective of the model is to make predictions that are close as possible to the actual RUL values. During training, the model learns the relationship between sensors behavior and engine degradation. A common loss function for this regression task is mean square error, one, where M is the number of training examples, RUL sub I is the actual remaining useful life, and RUL hat sub I is the predicted value. During training, the model tries to reduce the difference between actual and predicted RUL. Before going next, let's dive into that diagram real quick. This diagram shows how remaining useful life is calculated. The x-axis shows the current operating cycle, and the y-axis shows how many cycles remain until failure. For example, if the expected failure cycle is 220 and the engine is currently at cycle 140, then the RUL will be 220 minus 140, and that will equal to 80 cycles. 80 cycles. This means the model should learn to use sensor data and operating condition to predict how many cycles are left before failure. So maintenance can be planned in advance. So now we can choose machine learning modules that are suitable for predicting remaining useful life. Linear regression is a baseline model, provides a simple reference point that can be used to compare more advanced machine learning methods. If a more complex model cannot significantly outperform the baseline, then the added complexity may not be justified. In this task, linear regression will use operating settings and sensor readings as input features and predict the engine's remaining useful life as a continuous numeric values. The main advantage of linear regression is interpretability. It is easy to understand, fast to train, and useful for identifying basic relationships between sensor values and engine degradation. However, jet engine degradation is often nonlinear, so linear regression may not capture complex interactions between multiple sensors. Therefore, it is used mainly as a starting point for comparison. Gradient boosting regression is proposed as the advanced model for this project. Unlike linear regressions, it does not assume a simple linear relationship between sensor readings and remaining useful life. This is important because jet engine degradation can depend on complex interactions between temperature, pressure, speed, fuel flow, and other sensor values. Gradient boosting works by building a sequence of decision trees. Each new tree tries to correct the errors made by the previous trees. As a result, the final model combines many weak learns into one stronger predictive model. For this project, gradient boosting will use the same input features as the baseline model, like operating settings and sensor readings. However, it is expected to capture nonlinear degradation patterns more efficiently and produce more accurate RUL predictions. Evaluation plan. The models will be evaluated by comparing the predicted remaining useful life with the actual RUL values from the test data. Since RUL is measured in operating cycles, the year is easy to interpret in a maintenance context. The main metrics will be MAE, RMSE, and R power of 2 score. MAE shows the average prediction error in cycles. For example, an MAE of 12 means the model is wrong by about 12 cycles on average. RMSE gives a stronger penalty to large errors, which is important because large RUL mistakes can lead to late or unnecessary maintenance. And our Power of 2 score shows how well the model explains the relationship between sensor readings and engine life. This evaluation will help compare the linear regression baseline with the gradient boosting model and determine which approach provides more useful RUL prediction for maintenance planning. Expected results and practical value. In practical terms, this prediction can support better maintenance planning. Instead of relying only on fixed schedules, maintenance teams could use RUL estimates to decide when inspections or part replacement are needed. This may help reduce unexpected failures, avoid unnecessary downtime, and improve the overall reliability of aircraft operations. The important thing to say here is that the model does not replace engineers. It just supports expert judgment with data-driven RUL estimates. Finally, after reviewing the expected benefits and limitation, we can summarize the main idea and value of the proposed system. And let's go next. And here's the conclusion. Estimating RUL is important because spotting engine wear early can help prevent unexpected breakdowns and improve safety. The NASA CMAPS dataset provides the run-to-failure sensor data needed for these machine learning tasks. Linear regression gives a simple and easy-to-understand starting point, while gradient boosting can model more complex, nonlinear relationships in the sensor's data. This system can help make maintenance planning more data-driven and proactive. Thank you for attention. Bye.